If you've done any previous research in deep learning, you've probably heard of the Tensorflow library. It's a very popular framework developed by the folks at Google, and they've been kind enough to make it open source and freely available to the world. So let's talk about what Tensorflow is all about and how it can help you construct artificial neural networks. The thing that kind of took me by surprise when I first encountered TensorFlow was that it wasn't really purpose-built for deep learning at first, or even for neural networks in general. It's a much more general-purpose tool that Google developed that just happens to be useful for developing deep learning and neural networks. More generally, it's an architecture for executing a graph of numerical operations. It's not just about neural networks. You can have any sequence of operations and define a graph of how those operations fit together. What TensorFlow actually does is figure out how to distribute that processing across the various GPU cores on your PC or across various machines on a network, and make sure that you can do massive computing problems in a distributed manner. In that respect, it sounds a lot like Apache Spark. If you've taken other courses from me, you've probably heard me talk about Spark. It's a very exciting technology, and Spark is also developing machine learning and AI and deep learning capabilities of its own. So in some ways, TensorFlow is a competitor to Apache Spark, but there are some key differences that we should talk about. It's not just about distributing graphs of computation across a cluster or across your GPU. You can also run TensorFlow on just about anything. So one thing that's special about TensorFlow is that I can even run it on my phone if I want to. It's not limited to running on computers in a cluster in some data center. That's important because in the real world you might want to push that processing down to the end user's device. Let's take the example of a self-driving car. You wouldn't want your car to suddenly crash into a wall just because it lost its network connection to the cloud now, would you? The way that it actually works is that you might push the actual trained neural network down to the car itself and actually execute that neural network on the computer that's running embedded within your car, because the heavy lifting of deep learning is training that network. So you can do that training offline, push the weights of that network down to your car, which is relatively small, and then run that neural network completely within your car itself. By being able to run TensorFlow on a variety of devices, it opens up a lot of possibilities about actually doing deep learning on the edge, on the actual devices where you're trying to use it on. TensorFlow is written in C++ under the hood, whereas Spark is written in Scala, which ultimately runs on top of a JVM. By going down to the C++ level with TensorFlow, that's going to give you greater efficiency. But at the same time, it has a Python interface, so you can talk to it just like you would any other Python library. That makes it easy to program and easy to use as a developer, but very efficient and very fast under the hood. The other key difference between TensorFlow and something like Spark is that it can work on GPUs. A GPU is just your video card, the same video card that you're using to play Fortnite on or whatever it is you play. You can actually distribute the work across the GPU cores on your PC, and it's a very common configuration to even have multiple video cards on a single computer and actually use that to gain more performance on clusters that are purpose-built for deep learning. Plus, TensorFlow is free, and it's made by Google. Just the fact that it's made by Google has led to a lot of adoption. There are competing libraries out there to TensorFlow, notably Apache MXNet, but TensorFlow as of right now is still by far the most popular. Installing TensorFlow is really easy. All you have to do is use the conda command in your Anaconda environment to install TensorFlow, or you can use Anaconda Navigator to do it all through a graphical user interface. There's also a TensorFlow-GPU package you can install instead if you want to take advantage of GPU acceleration. If you're running this on Windows, I wouldn't go there quite yet. I've had some trouble getting TensorFlow GPU to work on my own Windows system. You'll find that a lot of these technologies are developed primarily for Linux systems running on a cluster, so if you're running on a purpose-built computer in a cluster on EC2 or something that's made for deep learning, go ahead and install TensorFlow-GPU, although it's probably going to be installed for you already. Let's talk about what TensorFlow is all about. What is a tensor anyway? Well, this is another example of fancy, pretentious terminology that people use to make themselves look smart. At the end of the day, a tensor is just a fancy name for an array, or a matrix of values. It's just a structured collection of numbers. That's it. That's all a tensor is. Using TensorFlow can be a little bit counterintuitive, but it's similar to how something like Apache Spark would work too. You don't actually execute things right away. Instead, you build up a graph of how you want things to execute, and then when you're ready to execute it, you say, okay, TensorFlow, go do this. TensorFlow will then go and figure out the optimal way to distribute and parallelize that work across your entire set of GPUs and computers in your cluster. So let's take a look here at the world's simplest TensorFlow application in Python. All this is going to do is add 1 plus 2 together, but it's a good illustrated example of what's actually going on under the hood. We start by importing the TensorFlow library. We're going to refer to it as TF as a shorthand. We'll start off by saying a equals tf.variable 1, name equals a. And all that is doing is setting up a variable in TensorFlow, a variable object which contains a single value 1 and which is going by the name of a. The name is what will appear in visualization tools for your graph if you're using that sort of a thing. But internally, we'll also assign that to a variable in Python called a. Then we set up a b variable that's assigned to the value 2 and given the name b. Here's where the magic starts to happen. We say f equals a plus b, and you might think that would put the number 3 into the variable f, but it doesn't. F is actually your graph. It's the connection that you're building up between the a and b tensors to add them together. So f equals a plus b does not do anything except establish that relationship between a and b and their dependency together on that f graph that you're creating. Nothing actually happens until we try to access the value of f, at which point TensorFlow 2 uses something called eager execution to actually execute that graph at that point. It will say, okay, I need to create a graph that takes the a variable, which contains 1, and the b variable, which contains 2, and add them together. It will figure out how to distribute that incredibly complicated operation, I'm being sarcastic, across your entire cluster. And that will ultimately print the value 3 in the form of a new tensor. So we have just created the most complicated way imaginable of computing 1 plus 2. But if these were larger tensors, dealing with larger datasets, or for example a huge array or a matrix of weights in a neural network, that distribution of the work becomes important. So although adding 1 plus 2 isn't a useful exercise to do with TensorFlow, once you scale this up to the many connections in a big neural network, it becomes very important to be able to distribute these things effectively. So how do we extend this idea to neural networks? Well, the thing with TensorFlow is that it's not only just made for neural networks. It can do things like matrix multiplication. And it turns out that you can think about applying all the different weights and sums that happen within a single layer of a perceptron and model that as just a matrix multiplication. You can just take the output of the previous layer in your multi-layer perceptron and do a matrix multiplication with a matrix that describes the weights between each neuron of the two layers that you're computing. Then you can add in a vector that contains the bias terms as well. So at the end of the day, you can modify this fancy diagram here of what a perceptron looks like and just model it as a matrix multiplication and vector addition. Go back and read up on your linear algebra if you want to know more about how that works mathematically, but this is just a straightforward matrix multiplication operation with a vector addition at the end for the bias terms. By using TensorFlow's lower level APIs, we're kind of doing this the hard way, but there are higher level APIs in TensorFlow that make it much simpler and more intuitive to define deep neural networks. As we're describing TensorFlow at a low level right now, its purpose in life is just to distribute mathematical operations on groups of numbers, or tensors, and it's up to us to describe what we're trying to do in mathematical terms. It turns out it's really not that hard to do with a neural network. For us to actually compute a complete deep learning network from end to end, there's more to it than just computing the weights between different layers of neurons. We have to actually train this thing somehow and actually run it when we're done. So the first thing we need to do is load up the training data that contains the features that we want to train on and the target labels. To train a neural network, you need to have a set of known inputs with a set of known correct answers that you can use to actually descend or converge upon the correct solution of weights that lead to the behavior that you want. After that, we need to associate some sort of an optimizer to the network. TensorFlow makes that very easy to do. It can be gradient descent or some variation thereof, such as Atom. We will then run our optimizer using our training data, and again, TensorFlow makes that pretty easy to do as well. Finally, we'll evaluate the results of our trained network using our test dataset. To recap at a high level, we're going to create a given network topology and fit the training data using gradient descent to actually converge on the optimal weights between each neuron in our network. When we're done, we can evaluate the performance of this network using a test dataset that it's never seen before and see if it can correctly classify that data that it was not trained on. One other gotcha. When you're using neural networks, it's very important to make sure that your input data is normalized, meaning that it's all scaled into the same range. Generally speaking, you want to make sure that your input data has a mean value of 0 and unit variance. That's just the best way to make the various activation functions work out mathematically. What's really important is that your input features are comparable in terms of magnitude. Otherwise, it's hard to combine those weights together in a meaningful way. Your inputs are all at the same level at the bottom of your neural network, and fitting into that bottom layer, it's important that they're comparable in terms of magnitude so you don't end up skewing things and weighting things in weird ways. For example, if I already created a neural network that tries to classify people based on their age and their income, age might range from 0 to 100, but income might range from 0 to a million. Those are wildly different ranges, so those are going to lead to real mathematical problems if they're not scaled down to the correct range at first. Fortunately, Python's scikit-learn library has a standard scalar package that you can use that will automatically do that with just one line of code. All you have to do is remember to use it, and many datasets that we use while researching will be normalized to begin with. The one we're about to use is already normalized, so we don't actually have to do that, but later on in the course, I'll show you an example of actually using standard scalar. We've talked about how this all works at a low level, and in TensorFlow 2, it's still possible to implement a complete neural network basically from scratch. But in TensorFlow 2, they have replaced much of that low-level functionality with a higher-level API called Keras. There is value in understanding how it all works under the hood first, so let's work through a simple example of a neural network using the lower-level APIs next. After that, we'll see how the Keras API simplifies common neural network setups and hides a lot of this complexity from you.